So I'm going to talk about the remarkable success of GlassBox learning when working with tabular data. Before I start, just want to thank, there's been a lot of students, including a few students from Cynthia's group, a lot of developers at Microsoft, doctors who have worked with us, faculty at different universities, and other researchers at Microsoft. So I just need to thank all these people because all the results are from us collectively. Hey, the workshop is right past, present, and future. I thought I'd start with a little history of machine learning. Perceptrons in the 50s, k-nearest neighbor in the 60s, decision trees in the 70s, neural nets coming back in the 80s again. Start seeing some principled methods like Bayes nets and SVMs in the 90s. And then there's the emergence of boosted trees, ensembles of trees, random forests, sort of in the end of the 90s, 2000s. Then around 2008, deep nets happen, which is really amazing, and they become clearly state-of-the-art for many kinds of problems. Surprisingly, on tabular data, though, most Kaggle competitions would still be won with gradient-boosted trees and random forests, and that remains true. And now LLMs have happened, which is really exciting. And so one of the questions is, where's tabular data going? Just for a second, though, let's take a fun detour. Little history of neural nets. First coming of neural nets was linear perceptrons, of course, no hidden layer. Then we added a hidden layer, but these were still very small neural nets, only one hidden layer, perhaps, and narrow hidden layers. Then deep nets happened, so suddenly we have hundreds of thousands, millions of parameters. And now LLMs have happened, and we're talking about billions and possibly trillions of parameters. So that's all really exciting. And there is no doubt that deep neural nets and LLMs are king of the hill, and perhaps will be for a long time, on things like text, cat images, acoustic speech, things like that. And now, even more exciting, wow, there's a Nobel Prize for neural nets. So this is really exciting, right? Machine learning AI has a Nobel Prize. So this is wonderful stuff. What's going to happen to us who are working in tabular learning? So where's that going? What's our history like? We think there's a chance that this GlassBox learning, the kind of simpler models that we're talking about today, is actually going to be the future for the next maybe 10 years. And that's because in some domains, you really have to use models that are interpretable. And data scientists, even if they don't have to, still benefit from using interpretable models. So there's lots of reasons to favor these GlassBox models. But many people still believe that there is a trade-off between accuracy and interpretability. If you want high accuracy, you got to be black box. If you want GlassBox interpretability, you're going to have to accept lower accuracy. The good news, as Cynthia said in her presentation, and I'll emphasize today as well, is this is just not true anymore for tabular data. It is still true in text. You still need a billion or maybe a trillion parameters with text, but this is not true for tabular data sets. And in particular, we have examples of algorithms now that are firing on all cylinders and performing just as well as the black box methods. And if anything, they're actually more intelligible than old things like linear and logistic regression, because those were too simple. So we now have things like generalized additive models, explainable boosting machines, neural additive models, GHOST, these optimal decision trees. There's a lot of things around now that are really, really doing quite well. And sometimes there is a tiny loss in accuracy. Sometimes there's no loss in accuracy. Sometimes these are the best model anybody's got. So that's exciting. Just to give you some evidence for this, this is AUC results on test sets for 10 different classification data sets. The average AUC for an EBM, which is a GlassBox model, is 0.866. Average AUC for gradient-boosted trees that have been optimized on these data sets is 0.866. We have essentially parity. Does not mean we always get identical accuracy on any data set for a GlassBox method and a black box method, but on average, we do about as well. And then take this with a grain of salt. I'm one of the co-authors, but Cynthia is one of the authors of this paper. So they also observe in their work, where they looked at a number of GlassBox models, that the best interpretable models often perform about as well as the best black box models of things like gradient-boosted trees. So that's really great. So, brief history of this stuff. We've got linear logistic regression, which has been around forever, right? Decision trees, I think, invented sort of simultaneously in the US, in California, and in Australia. We've got generalized additive models invented at Stanford, okay, and that's what I'll be talking mainly about today, and Cynthia also mentioned them earlier. In healthcare, they've been using things like simple nomograms, where you have a couple features with scales and you put a straight line across them, things like that. And they've been using these additive tables, what Cynthia, I think, called score models. They've been using these for decades, and in fact, there's hundreds of these published on the web, and dozens of them are in daily use everywhere. So the odds are, if you've gone in for healthcare, somebody has used one of these models on you. So these are very simple additive models. There's these generalized additive models with pairwise interactions that we've been working on since rebranded by Microsoft as explainable boosting machines, since they didn't like GA2Ms and needing an exponent. There's these optimal decision trees that Cynthia and her group has been working on. They have a number of algorithms for generating models that are simple enough but accurate enough. And then there's these neural additive models where we can do GAMs, but now with neural net instead of boosted trees. And then later today, we'll have a talk on GAMformer, it's amazing that you can train GAMs now with transformer models, which is really incredible. So there'll be a talk later this morning on that. Okay, let me tell you what these things are. Hey, linear models, we're all familiar with that. Gold standard perhaps for interpretability, even though they're not as interpretable as everybody thinks. Not very accurate, and that's because they're linear. And sometimes they even get the sign wrong. So be afraid of these things if your data is complex. Hey, black box, we've got a lot of them. They're really good. They're black boxes in part because they're complex in a way that we really can't decode as humans. And these things, if you do open them up, they're more likely to have learned spurious effects inside of them. So if you use SHAP to understand a black box, you'll often see some things in there that are questionable, that you wonder if it's real in the data. In the middle is maybe the Goldilocks sort of set of models. These are things which are restricted in complexity one way or another. But they can perhaps model nonlinearities, they can be multimodal, they can be complex. And what's surprising is not only can they be as accurate as the black box models, but even more surprising is they can be more interpretable than linear and logistic regression to experts. And that's because the experts see detail which makes a lot of sense to them. So that detail is good, and it's missing sometimes in the linear models. Now, there are ways to make linear models do many of the things that these models do, but it takes an awful lot of human expertise often to achieve that, whereas these things are sort of doing it in machine learning fashion, fully automagically. Just to give credit where credit is due, this is Trevor Hasty's thesis in the late 80s at Stanford. Rob Tibshirani's his advisor. And they invented these things. If you read their book, his thesis from 1989, they invented these things for all the reasons we want to work with them. Our main contribution is to sort of modernize these things, use modern machine learning tricks to really make them perform as well as we can. And we've got massive horsepower and big data sets now, things that they never had. So that's going to be our contribution. And surprisingly, if you really do these things carefully and use modern tricks, they really do perform as well as black box methods, which is great. Let me just briefly show you what these things are. Everybody knows what a linear model looks like. Full complexity models, let's not worry about the functional form of them. It's just, a billion weights sitting somewhere. Here's the simplest generalized additive model. It's a function of feature 1 plus another function of feature 2 plus a function of feature 3. And addition combines these things. So we're going to learn these shape functions that predict, say, risk or income or something as a function of these features. But these functions are restricted to being functions of individual features at a time, with addition combining them. Now, we can make that model class richer by having functions of individual features here, but we can have sum of functions of pairs of features, and now we can do pairwise interactions. We can go further and have triples of features and do three-way interactions. Most of the time, we'll stick with main effects, functions of individual features, and then just a small number of the most important pairwise interactions. And we'll restrict ourselves to that model class because it remains very interpretable. I'm going to show you some examples of these. Okay, apologies if you have seen this before, but it is one of the best examples that I've got that's easy to explain. So this is a pneumonia data set. It's got 46 features in it. This model class is a function of a feature, 46 features. We're going to have 46 functions. We'll throw in 10 pairwise interactions. So we've got 56 functions. Let me show you what this looks like from a high-level view. Is imagine you've got 56 graphs like this. Each of these is a function. We're trying to predict your chance of dying from pneumonia, so we're predicting mortality here. And this is a function of mortality risk as a function of age, plus a function of your asthma, whether you have it or not. Down at the bottom, your blood urea nitrogen. And the way you use this is you find the patient's age on the x-axis, you read off some contribution to risk, a score on the y-axis, write that score down, go to the next graph. 56 terms, you're going to end up with 56 numbers. We'll have an intercept, so 57 numbers. Add them all together, and that's a score. And in this case, the higher the score, greater the probability of mortality. The lower the score, the healthier, the safer the patient. And it's important in GAM algorithms, these graphs are all learned together, to work together. There is no multiple counting of evidence. This is not marginalization. This is a fairly sophisticated round-robin algorithm, parts of which were actually created by Trevor Hasty in 1989 that does this. And then what you do is you take the score and 1 over 1 plus e to the minus score. That's logistic regression. In fact, if this had been logistic regression, the graphs would all look like straight lines. Actually, they'd all have intercepts at 0, but ignore that. They'd all look like straight lines, and you just have a linear function up in the exponent here. But instead, we have these nonlinear graphs that have been learned by the model. So in some sense, we have these nonlinear functions up in the exponent. Okay. All right, let's drill into one of these, that first graph of risk as a function of age. This is what the model learns by itself. Down is lower risk, up is higher risk. Let me just interpret this for you. Well, it's good to be young, and the model says young is sort of everybody under 50, all equally low risk. Not too bad to be in your 50s, maybe into your mid-60s. Surprising rapid rise in risk at around 67, 68, 69. This is sadly a retirement effect. We see this mainly in the United States. We don't see this so much in other countries. Lots of things, including your healthcare provider, probably change when you retire. So sadly, retirement isn't as good for you as you might have thought, at least not if you have pneumonia. Then, of course, it kind of sucks to get old and go into your 70s, into your 80s. Surprising step function rise in risk at a very round number at 85. Surprising flatness in risk through the upper 80s and 90s, and then an even more surprising drop in risk, like right at 100, 101. The rise in risk at 85, there's nothing in healthcare policy in the US that says you should treat patients who are 86 different than patients who are 84. What's happening is people over 85 are considered very elderly, especially in this old data set, and they're getting less aggressive care over 85 than they would have gotten if they had been younger. The opposite is happening over 100. You've got a patient, maybe they're 2 or 3 months away from their 101st birthday or something like that, and the doctors will do everything they can to get them to that 101st birthday. Like they're going for the record, and the doctors assure me that that's what really, really happens. So if it's a treatable illness, they will do this, and they will fight tooth and nail to get the patient past it, especially if the patient has made it to this magic 100-year-old centenarian kind of thing. Okay. This model is the most accurate model anyone's ever been able to train on the data, and I just told you this nuanced story from one of the graphs. So remember, there's 56 graphs in this model, which I can't show you. There's something else going on here, which is the graph is not an approximation of some more complex model in the other room. We used millions of decision trees in a boosting algorithm to generate these graphs. Once we have the graphs, we throw the trees away, and we actually make predictions with the graphs. Now, how many of you think a 105-year-old is actually biologically lower risk than a 95-year-old, which is what the model says? Well, the doctors say, that's not true. We understand why that's a statistic in the data, but biologically, that's not true. So we can edit the graph, because the graph is the model, and if we edit it, it will do our bidding. Okay. That's an amazing power that you get from simpler models, is that you can not only see problems in the models, you can often correct the models in the problems. Let me show you some other things the model has learned. Remember, these are all pneumonia patients. Ooh, having asthma is good for you if you've got pneumonia. Having heart disease and recurring chest pain is good for you if you've got pneumonia. And remarkably, having a kind of wheezing that indicates you have a blocked airway is good for you if you've got pneumonia. None of these are true biologically. But the statistics are true in the data. Why are these things good for you? Well, all of these things cause you to get to care faster. And once you get to care, they cause you to get better quality care than you would have gotten if you didn't have these conditions. So what's good for you is your response and the clinical response to these conditions. It's not that biologically these things are good for you, okay? So this is standard statistical confounding, what's known as treatment effects, okay? Happens in every data set we look at. There are ways of dealing with this. This is not a new problem. Statisticians, of course, have been aware of this problem for many, many, many decades. We see this all the time. By the way, if a black box model is trained on this data, it will learn these same effects. You'll just never know it's there. GlassBox has the advantage that you get to see that it's there. The cool thing is these are editable models. We can flatten the effects when the clinician says, oh, that's not real, get rid of that. Or even better, the clinician can say, you know, actually, some of these people are at higher risk. We want you to draw in higher risk. And now we're really using human expertise in the loop to modify the model in a way that is not justified by the data. That's very, very important. So we're going to talk about that for a second. So that's a big deal. Anytime you overrule your data. Now, you might just say, oh, you should go get better data. You're not allowed to get better data for any of the things I just mentioned. You're not allowed to do randomized clinical trial for asthma, for heart disease, for being over 100. You can't do any of the things you would have to do to get the right data. All data will have these problems. You can throw in the treatments if you know them into the data set, and sometimes that helps. Turns out the better healthcare is at being consistent at providing the treatment, the harder it is to learn what the model should have learned for patients who might not have received, what their intrinsic risk is without the treatment. So it's complex. We don't have time to, that's like a whole afternoon session all by itself. Okay, so we've created an editor specifically for doctors, but anybody can use it. And in fact, 2 doctors from NYU are co-authors on this work, called Gam Changer, which is like a Photoshop for working on GAMs, okay? And it lets you take things like, here's a noisy risk curve as a function of age, and all of us don't believe that noise is intrinsic to the model, that we really wanted it to learn that. So you can go into Gam Changer and you can say, you know, I'm pretty sure it should be a monotone increasing risk with age. And it will automatically use something like the pair-adjacent violators algorithm to find the optimal, the smallest edits to the model it can do in order to achieve monotonicity. Interesting thing when you do all these edits. Now remember, it's an additive model. It thinks that a 105-year-old with a history of asthma who had a heart attack 3 years ago and who now has advanced pneumonia and stridor is actually very low risk. And they actually are low risk in the training data. And our test set is a random sample of the training data, so they're actually low risk in the test sample as well. But this is not true, right? These are very high-risk patients. So actually, when we do these edits to correct the model, it turns out the accuracy on the test set actually goes down often. Now, getting rid of noise like this can improve accuracy, okay? Because this is acting, as Cynthia said, as a regularizer when we do this. And this can improve accuracy. But often we will see accuracy, however you measure it, go down a little on the test set if it's a random sample. So that's a very important thing. This is a cool tool. It gives you all sorts of things. We force people to document their edits. They better be very confident of their edits, or else they should not be overruling the data. Here's the most important take-home, though, is that accuracy is not equal to correctness. And I guarantee you, you always want correctness for your domain, for your problem. You don't want high accuracy on retrospective test set. You want high accuracy on prospective future data, and you achieve that with correctness, not by test set accuracy. So that's very, very important. Let me just show you a fun thing that the model learns. This is still pneumonia risk. This is blood urea nitrogen, blood test you've all had. Low blood urea nitrogen is a sign of health. 2 interesting things. Notice that risk flattens right at 50 because patients are being given a medication. Risk peaks at 100. Notice these are round numbers. This is very strange. These are treatment effects. And that's because patients are being given a stronger treatment, dialysis. And dialysis is so effective that by 120, all the patients who are eligible for it are getting it, okay? And their risk is actually lower than that of healthier patients, say at 90, who might not be getting dialysis. And that's really unfortunate. So one, it's cool that we can see the treatment effects and thresholds in the graph, but we can also do a kind of what-if causal analysis with this kind of model. Now you have to be careful. The model is not causal. Okay, this is not causal learning. However, the human in the loop looking at the model, that can be causal if they work well, if they work hard. So that's what makes this causal, is the human reasoning added to the model, possibly with extra experiments that then have to be done. And by doing that, we can conservatively estimate that the risk curve would look no worse than this red line. And we have good reasons for that, which I can explain if you're interested later. And that means in the US, just by making this simple change to a treatment threshold, we would save maybe 2,500 to 5,000 lives in the US, maybe 50,000 lives worldwide per year. And that's by making one change to one treatment threshold for one treatment dialysis for one condition, pneumonia, based on one test, blood urea nitrogen. So it's kind of amazing what you can see sometimes in these models. And by the way, I would never suggest changing how healthcare is provided by looking at a single graph in a single data set. And yeah, there's an awful lot of diligence that must be done to do this right. Okay. Treatment effects all over in data. This is blood pressure. I assure you that once your blood pressure is over 160, the higher it is, the worse off you are. However, if you hit certain treatment thresholds, like 180 hypertensive urgency or 200, which is a very high round number, you get treated more aggressively, and that lowers your risk. I mean, the good news is we're seeing treatment effects, which means treatments are effective. That's great. It means healthcare has things that they can do to help you. So we see these effects all over the place, and you have to reason about these things and decide what to do. Let me give you another example of just something interesting we've run into. This is mortality in the ICU. This is PF ratio, a measure of how oxygenated your blood is. And the graph is roughly right. Poor oxygenation near 0 is high risk, and oxygenation near 1,000 indicates low risk. There's a funny spike. That spike, strangely enough, is very low risk. So it's as low risk as the healthiest patients. And it turns out before we got the data, somebody had imputed the missing values with the mean. And that's where the mean of this feature happens to be. And 60% of the patients are missing this measure because they pinched your finger. If pink returns quickly, you don't need the test. You're doing fine. So this is a very interesting problem. Now, you start thinking, well, you know, imputation with the mean, that's so stupid. Why would anybody do that? Turns out the other methods, like k-nearest neighbor and random forest imputation, are even more stupid for this particular feature in this data set. They will injure more patients, and that's because most of the imputed values end up being in this unhealthy region, even though these are very healthy patients. That's why they're missing this value. It ends up imputing that, and it ends up reducing the entire risk curve in this region, and it will have huge impact on the people who are actually at high risk in this region. So this is a terrible thing. We have not yet, for this data set and feature, found any imputation method that actually works well here. So it turns out, and this is work with one of Cynthia's students as well, and it turns out that it's completely changed now, having GlassBox learning, how we think about and deal with missing values. Now what we do is we try every trick we can, we retrain the model each time, and we compare the graphs, and we find the solution that looks best, or often least worst. So that's what we do. So this is very important. Everything you've heard about missing values, they're good tricks, but you shouldn't believe them. And you shouldn't believe that random forest imputation, because it's so popular, is always going to work. In fact, accuracy goes up when we use random forest imputation, but correctness goes down. So really, really important to wrap your head around that. Okay. Let me just briefly show you these neural additive models. This is joint work some people at Microsoft, at Google, and with Jeff Hinton at Toronto. How do we get a neural net to do these additive models? Well, what we do is we have a big subnet. It can be deep and wide, but it can only see feature 1. And it's trained at the same time a subnet that can only see feature 2 is trained. So we have a sort of separate, disconnected subnet for each feature, all learned in parallel, to add together to create a score that, in this case, for classification, goes through a sigmoid to predict a probability. So this thing is forced to learn an additive function without any interaction terms. And we can add interaction terms if we want. So this model is forced to learn a GAM. And then what we do is we train the model and we draw the graph for each subnet, and we throw the neural net away. Just like we threw the trees away, we throw the neural net away. Okay, so this is great, and it works surprisingly well. So here's NAMs and EBMs on some 3 classification data sets, 2 regression data sets, and they're basically neck and neck. And part of the reason they're neck and neck is because the main constraint is actually coming from the model simplification architecture, the gamminess of the model, not from the learning method. So that's really great that we can do this with neural nets as well. Because there are some advantages to neural nets that boosted trees don't have. Like it's easier to do multitask learning and things like that with neural nets. Okay. One of the weird properties of having these very simple models is that they tend to protect privacy because they don't really do conjunctions of features, which is how you often leak privacy. So we were able to turn these into provably differentially private models by just making very tiny changes to the algorithm. And the amazing thing is, we're not experts in differential privacy. We just made small changes to satisfy the theorem so that we could prove they were differentially private. And right away, they became, for tabular data, the most accurate differentially private algorithm on the planet, which is really kind of remarkable. So other algorithms, as you increase privacy, the accuracy goes down dramatically. They fall off a cliff. It's not true for these things because they were already almost approximately private to begin with. Okay, one last thing. What makes a model intelligible to human often makes it intelligible to LLMs. That's very interesting. So you can ask an LLM to summarize these shape functions, like, is that graph monotone? Tell me something about it. You can ask it if it has domain knowledge, which it does have a lot of domain knowledge about medical stuff. You can say, oh, this is a graph of albumin, here's the graph. And it'll tell you something like, well, this includes negative albumin levels, which are physiologically impossible and might represent errors in your data. Turns out those are missing values, but we're glad it caught that. Here it says, it's really surprising that risk from creatinine log odds of death drops after about 5 in the graph, because that's not true. What's happening in this graph is dialysis is also being given at 5, and it's incredibly effective. Otherwise, risk would keep going up. So it's great that LLMs can help us with this. And we've done a study called 4 doctors and an LLM walk into a bar to compare these guys. So we've compared 4 doctors with an LLM at generating these anomaly detections and explanations. And we've compared the number of detections, how much they agree with their detections, how much they agree with the explanations. And the old LLM GPT-4 was nowhere near as good as the doctors, but it was already good enough to act as a useful safety net. And the new LLMs are getting much, much better. Okay, every data set, I guarantee you, every data set you've ever done machine learning with, and it could be images as well, has these sorts of problems in it. Treatment effects, missing features, confounding, it's everywhere. GlassBox learning for tabular data is ready for prime time now. You should be using it. So little or no loss in accuracy. You can edit models to correct mistakes. You can often guarantee privacy. You can create an LLM user interface, and it can help you find anomalies in the model. It can help you explain the model to people who maybe don't want to look at graphs. And you can even train these things with now transformers. So Andreas will talk about that later. Just a take-home message, accuracy and correctness are not the same thing. I guarantee you, you always want correctness, and you really need GlassBox intelligibility of some form to be able to judge if your model is correct or not. Okay, thank you.
Whenever I hear the terms GlassBox, interpretable model, I wonder, what is the interpretation? And your interpretation seems to be that whatever feature you observe a non-zero coefficient or a non-zero function, or whatever feature for which your tree branches, you assume to interpret this as having a relationship to the target. But I can tell you this is not true.
This is a great question. And let me just give you 2 quick responses. I agree with what you said. Let me just give you 2 quick responses. One is the classic thing we've all heard, which is, every model is wrong, but some models are useful. This is definitely true of this sort of stuff. We don't expect these things to be true. And in fact, the graphs will change if you just add or subtract features from the data set, which means no one graph is ever correct in some cosmic way. But the thing is, when I say GlassBox, what I really mean is something very simple, which is the model is telling us exactly how it makes predictions. And that is absolutely true. There's no approximation here. If you can read the graphs to 3 decimal places, you can make the predictions the model makes to 3 decimal places. That is what's absolutely true of GlassBox. It's only when the human gets in the loop, when the human has sufficient expertise, often that requires both data scientists and human experts working together. It's only when the human is in the loop, you do due diligence, you'd probably do extra experiments. It's only then that you start to believe some of the connections between what the model is showing you about how it would make predictions and the real world. And sometimes human experts are very good at saying, oh, I know what causes that. That's because of this policy that we have, you know, whatever. And other times, you never figure it out. Like, you put on your Sherlock Holmes hat, and, you know, a month later, you're still in the dark, and you don't know. And there can be things hidden in the graphs, too, that you don't even see. Like, I'm talking about jumps and bumps and things like that. There are things that are happening that aren't jumps and bumps. Go ahead.
Can I make it more concrete? So
yeah.
My point is that you could have a feature that has nothing to do with your target. You could have correlated noise, a factor that has nothing to do with your target. It affects 2 of your features. Then what the model is doing, it subtracts those features from another to denoise them. And this explains some of your observations. This explains why you have these seemingly negative correlations, but these are not correlations. These are negative coefficients.
Absolutely, and we do see interesting effects among correlated features. In fact, one of the most interesting effects that we often see is not the specific one you're talking about. We often see that the same information is essentially presented among a small set of correlated features, and the model essentially divides its explanatory variance reduction, you know, among those features in a way that can make each one harder to interpret. So correlation is definitely the enemy here, especially correlation in noise. And that's why I say it's like you can't just expect a doctor to figure this out. You need a data scientist. And as I said, sometimes you will never figure it out. But hey, the world's difficult, right? Yeah, I mean, there's no magic. Yeah.
Happy to discuss later.
Yeah, this is great. Thank you.
I did get a bit nervous, though, when you talked about editing
these
elements.
Yes.
Particularly because of causality and the idea of survivor bias. So the classic example that in my head is infant mortality and smoking for a given birth weight. If you have a low birth weight baby, those that had a mother that smoked actually do better than those that didn't.
Yes.
Because they're small, not because they have a comorbidity, they're small because they were starved of oxygen, but they've adapted. And so if you changed the treatment of those babies and gave them more treatment, you'd actually be taking resources away from the babies that needed more attention because they have the genuinely dangerous comorbidities. What do you think of that?
This is great, and I'm glad you said this. And by the way, we see the same thing in the pregnancy data we look at, and we can talk about this. You know, one of the effects is if the mother smokes and the baby is smaller, then delivery will actually be easier, and an easier delivery is better for both the baby and the mother, but it's not in the long term better for either the baby or the mother that there was smoking. So there's all these interesting effects, and you wouldn't want to like say, oh, go from 1 pack a day to 5 packs a day. You know, that would be a bad causal intervention. So we definitely see these sorts of effects. You definitely need expertise to figure these things out. You should not, and by the way, every black box model you train on the data will be learning exactly the same thing. So you know, shame on you if you're not putting the glasses on so that you can at least see some of these problems. And you're never going to get all of them, but you can do better than you would do if you didn't have glass box interpretability. You're exactly right, though, and you've got to be careful. These are not causal models. It's only human expertise combined with looking at the models that in some cases can come up with what are clearly the right causal explanation for what's happening, and only then are you happy to edit the models. But half the time when I talk in front of a CS audience and I talk about editing the models and overruling the data, like half of the audience wants to kill me. It's like, who the hell are you to do that? And all I can say is, well, do you really want to leave that being over 100, being asthmatic, having heart disease and having stridor, you know, advanced pneumonia are all good for you and that those are ultra low risk patients? Well, that's the worst thing you could do, is to leave those in the model. So even if we can't get the edit perfect it's better to do the best we can and make the model safer and more reliable. And I guarantee you, in that case, the model will have higher accuracy in the real world when you deploy it.
Okay,
Yeah, it's a huge can of worms. If you want to do research now, do it in editing models because, man, I think that's a whole industry that needs to be, yeah.